Okay, so we are going to talk about the solubility product post lab. So in this lab, you ran a reaction, or actually you presented solutions of silver chromate. You did a calibration curve to determine how much chromate was present. And using that information, you did three solutions, A, B, and C. B and C you can see here. A was with nothing. The sodium nitrate was as a stabilizer. So in any event, we were able to determine the KSP from experimental data based on that calibration curve. So, for the discussion questions, solutions B and C contained a common ion. So, solutions B and C contained really, again, we can always ignore nitrate and we can always ignore group one. So, solution B contained silver plus ions, and solution C contained chromate ions. So the question is, should the presence of the common ion affect the KSP, and why or why not? So let's take a look. So first of all, we always need the equilibrium. So this is solubility products. So we have a solid dissociating into two silver ions and one chromate ion. Now, a common ion will shift the reaction. So by increasing the concentration of Ag plus, okay, that causes a shift, according to Le Chatelier's, to shift it back towards, in this case, it's going to equal a shift in the direction towards the silver chromate, reducing reducing the amount of ions based on the addition or the presence of that extra silver, and creating more solid. It's going to decrease the solubility. But the question wasn't whether it decreases or increases solubility. The question is, does it affect the magnitude of KSP? And the answer is pretty simple when it comes to KSP. KSP is a constant, K is a constant, and the only thing that affects it is temperature. So yes, common ions will shift the reaction, but will not change K. In fact, the only thing that can change K is temperature. So temperature is the only thing that will actually shift K. So K is going to remain constant. You are going to get a shift, or really an adjustment. So you're going to have, because you have more silver, you're going to have less chromate in order to equal K, but K will remain constant as it always does. Okay, so moving on. So problems. Okay, calculate the mass in grams of silver chromate that will precipitate out. Okay, so mass in grams of the silver chromate that will precipitate out. All right. 50 mils of silver ions and 40 mils of chromate ions based on their concentrations. Assume that is, so essentially what this is asking is, okay, if we ran a reaction where I combine together silver and chromate, we know that it's going to form a solid, and we know it's two silvers to one chromate. So this is the reaction that's being run here. And this is really a limiting reaction problem. This is a stoichiometry problem with solutions. We're trying to determine how much silver chromate would be produced by the presence of these things. So if we start with, let's say, the K2CrO4 solution, again, really what we're talking about is this is just the chromate solution. Okay. We started with 40 mils. That's the quantity that we use. So if this were stoichiometry and we had a solid, we would use grams, uh, 40 milliliters. Of course, we're going to convert this to liters. So let's just start with liters, 0.0400 liters times fraction. I want liters to go away. I want moles to remain. We are going to always use the concentration of the silver chromate, or the potassium chromate here. Always use concentration as a conversion factor. According to the problem here, 1 liter is equivalent to 0.10 moles. So at this point, liters cancels, and I am left with moles of chromate. Again, I'm going to ignore the potassium part here because really we need to focus on just the chromate. All right. So times fraction, I want moles of chromate to go away. This is where I'm using my molar ratio. And I want to convert from moles of chromate to moles of silver chromate. So for every 1 mole of chromate, I have 1 mole. So it's a 1-to-1 ratio. That makes life easy. 1-to-1. Moles of chromate cancel at this point, and I would have moles of silver chromate. Well, now the last step in this, I want to get rid of moles of silver chromate, and I want to be left with grams of silver chromate. And we do that through molar mass. So we need the molar mass of the silver chromate, Ag2CrO4. We determined that to be 331.730 grams per 1 mole. Moles of silver chromate cancel, and now I just simply do the math. So multiply this out. I end up with 1.3 grams, or I should say, yeah, 1.3, because I'm going to round to 2 sig figs because the concentrations have 2 sig figs, so my answer has to be 2. So uh, the amount of silver chromate produced by the chromate solution, the potassium chromate solution, I would produce 1.3 grams of silver chromate. All right, so what happens if I start with the silver nitrate solution? So here I'm going to start with the silver nitrate solution. And again, I don't really care about nitrate. What this really is me looking at silver ions. So I'm starting with silver. Again, we want a quantity here. So we have 50 mils of the silver nitrate solution. So 0.0, well, 50 mils. Let me just do it this way. Milliliters. Of course, we're going to talk about this in liters. So 0.0500 liters times a fraction. Again, I'm going to need the concentration of my silver nitrate here because I want to figure out moles of silver. So liters to go away, moles of silver ions to remain. For every 1 liter, the concentration was 0.2 molar. So 0.2 molar, 0.20 moles of AgNO3 for every liter. Liters cancels, and I'm left with moles of silver times fraction. I want moles of silver to go away, and I want moles of my silver chromate to remain. So for every 2 moles of silver chromate, I have 1 mole of Ag2Cr. Again, this is molar ratio from the balanced chemical equation. All right. So at this point, moles of silver ions goes away. And this last step, moles to grams, this is the molar mass. So for every, was it 331.730, oh, 0.730 grams per 1 mole. Moles cancel, and I'm left with grams. Rounding to, well, 1 sig fig would give me 42 or 41.5, so 42 grams of Ag2CrO4. So which one's limiting? Clearly, this one right here is limiting. I'm going to produce 1.3 grams of silver chromate. So we see that the chromate solution K2CrO4 is limiting. So we should end up with a maximum of 1.3 grams of silver chromate in this solution. That is the idea. Okay, so the idea being here is we're going to consider it completely insoluble and figure out what that limiting reactant is. Okay, moving on. So calculate the number of milligrams of silver chromate that would dissolve in 400 mils. Okay, so here we go. Number of milligrams of silver chromate that would dissolve in 400 mils of distilled water. Okay, so a couple of things here. We are looking for milligrams, so we're going to use millimoles and milliliters here because it's going to make life much simpler. Um, when you're using your average KSP from the experiment. So again, I'm going to give you an average that I had at some point for one of my previous. So my KSP average that I'm going to be using. I rounded it quite a bit too, so make sure you have the appropriate number of sig figs for you, but I'm going to round it to 1.5 times 10 to the negative 11. Say 1.50 times 10 to the negative 11. I rounded it quite a bit, but again, you're going to use your number from your experimental results. So from my experiment, I got 1.5 times 10 to the negative 11, so that's what I'm going to use. So calculate the number of that would dissolve based on your average KSP. Okay, so let's just set this up. Anytime we're looking at an equilibrium, we need three things. First, I need the equation. Ag2CrO4 is in equilibrium when that's a solid, is in equilibrium with 2Ag plus CrO4 2 minus. Both of those are aqueous. I'm going to set myself up an ice table here. Molarity, initial change, equilibrium, and I only really care about the equilibrium numbers in the end. There we go. And I also need my K value. My KSP is equal to the concentration of my silver ions. I don't need that, do I? Concentration of silver ions squared, concentration of my chromate ions. There we go. All right, so we've got everything we need. Let's plug in what we have. I know my KSP is 1.5 times 10, 1.50 times 10 to the negative 11. I know I don't really care about the silver chromate because it's a solid. It doesn't appear in the equilibrium expression. I didn't start with any silver ions. So I'm going to gain 2x of my silver ions. I'm going to gain x of my chromate. So at equilibrium, I should have x and 2x, meaning 2x squared and x amount of chromate. There we go. So let's process this and solve for x. So 1.50 times 10 to the negative 11. 2x squared becomes 4x squared times x would give me 4x cubed. Okay, 4x cubed. I'm going to divide both sides by 4. And I end up with 3.8 times 10 to the negative 12. I probably should have 3 sig figs, but it looks like I limited myself here. And then I'm going to take the cube root to solve for x. 1.6 times 10 to the negative 4. Okay, so something that we know. Calculate the average amount that's going to dissolve in 400 mils. Right now, this value, and I always tell my students, x, whatever you solve for x, because that is always a 1-to-1 ratio. So for every 1 silver chromate, I am producing 1 chromate. Okay, so for every one of these that dissolves, dissolves or dissociates, I'm producing 1 chromate, and that's my X value. So X is essentially how many of those I lost. So my 1.6 times 10 to the negative 4, that right there, your X value is your molar solubility. So my molar solubility is equal to X. You can just simply say it's equal to X, which means 1.6 times 10 to the minus 4 moles of Ag2CrO4 per 1 liter of solution. This is a concentration to some degree, but per liter of solution. So that's my molar solubility. For every 1.6 times 10 to the negative 4 moles, I should be able to dissolve in 1 liter of water. So this is essentially a concentration. So we are going to start with 400 mils because that's how much I wanted to know it was going to dissolve. 400 mils times fraction. I want the milliliters to go away. Actually, I want the liters to go away and I want moles to remain. And so here's the part where if I plug in the same prefix for both, it's going to have the same ratio. So 1.6 times 10 to the negative 4 moles per 1 liter, or 1.6 times 10 to the negative 4 millimoles per milliliter. It's an easy way of dealing with milliliters because we always kind of deal with milliliters. Milliliters cancels, and at this point, I would have millimoles of Ag2 CrO4. So take it one more step. So if my unit is millimoles per milliliters times fraction, I want moles to go away. I want grams to remain. But again, if I put milli in front of both of these, that is just the molar mass. 331.730 milligrams per millimoles. Millimoles cancels, and I'm left with milligrams. Do the math, and around 21, looks like I just did two sig figs, 21 milligrams of Ag2CrO4. So there we go. That is how much should dissolve in 400 mils. Great. So that's the idea here, is we are simply saying, look, how much molar solubility do we have, but we only have putting in 400 mils. All right, next up, using your average KSP, okay, calculate the number of milligrams of Ag2CrO4 in, okay, so in a solution. So again, we're calculating the same thing. Number of milligrams of Ag2CrO4 in 400 mils. Okay, same solution, but instead of being just pure water in this case, it already has some potassium chromate present, which really ultimately means what? It means the concentration of the chromate is equal to whatever that is, 0.00150 molar. Because chromate, there's one chromate for every one K2CrO4. So I know the concentration of chromate. So I don't need to redo the ICE table because I already have kind of all that information. So KSP will not change because temperature did not change, is going to be the same silver ions squared times chromate ions. Okay, my KSP I know of 1.5 times 10 to the negative 11. I still know my silver ions should be 2x, but instead of me having 0 chromate to start, I actually have this much chromate to start. So that's going to dwarf what X is, or that's going to overshadow what X is. So X is actually going to be equal to the starting concentration. And so instead of plugging in X for chromate, I am going to plug in that concentration that we started with. So the concentration is 0.00150 molar. There we go. And now we can work through this. So I'm going to divide both sides by 0.0015, and I'm going to square the 2x. So on the right, I'm going to have 4x squared, and I move the 0.00 divide by 0.0015, and a 1.0 times 10 to the negative 8. Okay, divide both sides by 4. 2.5 times 10 to the negative 9 is equal to x squared. Take the square root. 5.0 times 10 to the negative fifth is equal to x. So before we continue, I have a common ion present. I already have chromate present. So that means this is going to decrease the solubility. We should see a decrease in solubility because the common ion is going to decrease solubility. Again, KH stays the same, but it's going to decrease solubility. So whatever I get here is for my milligrams should be less than 21. That's how we kind of know the chemistry makes sense, and the chemistry is chemistrying. All right, so 400.0 milliliters times fraction. I want milliliters to go away, and I want to be left with millimoles. Again, we're using the trick where I put milli in front of moles and milli in front of liters, and that is my value of X. And again, remember, X is just simply the molar solubility in this case. So 5.0 times 10 to the negative 5 millimoles per 1 mil. Milliliters cancels, and I would be left with millimoles of Ag2CrO4 times fraction. I want moles to go away, grams to remain, but again, we're going to put milli in front. 331.73 I'll zoom in. 730 milligrams per 1 millimole. Millimoles of chromate cancels, and I am left with 5. So do the math, 6.6 milligrams of Ag2CrO4. So we end up with only 6.6 grams. And again, the solubility should decrease, and it absolutely did. 6.6 from 21. So it makes sense because I already had a common ion present, so I should produce less. Okay. What is the equilibrium concentration of silver ions? Okay, so we know silver is equal to 2x. Okay, so that's what we know. And so we're going to pull that information down. We know that the concentration of silver plus is equal to 2x. So 2 times our x value, which is 5.0 times 10 to the minus 5. Okay, so the concentration is 1.0 times 10 to the minus 4 molar. And we're going to highlight that. That is the concentration of the silver ion. Don't get caught up in all the different numbers you have. Just recognize that it really always comes down to the concentration and solving for X. So here we go. That is the concentration of your silver in solution, silver ions in solution. All right, so next one. Will strontium chromate precipitate? Okay, so that's just simply the question is, will strontium precipitate? Okay, and this is a question of K versus Q. Okay, when 1 mil of strontium nitrate is added to a solution from 3 above, so we are looking at 3 added to the solution from 3 above. Okay, so let's write out the equilibrium expression, SrCrO4 solid is Sr2 plus the chromate, CrO4 2 minus. There we go. And so that is going to provide us with a K. So we need at least these two things, KSP, which is equal to concentration of Sr2 plus the chromate ion. And we're given a value for this. Yes, we're given a value of KSP, which is important right there. Okay, so the value of KSP for this is, so the KSP is 3.6 times 10 to the minus 5. We do not know if we're at equilibrium. So what we're actually at is we have to decide what is our current Q position, as in how many ions do I have in solution. So my Q is strontium times chromate. Nothing changes. It's the same exact expression, only not at equilibrium. So I got to solve for Q and then go from there. So what is the concentration of my strontium? Okay, so 1 mil of 0.120 strontium nitrate. Again, I don't care about the nitrates part. It's really just strontium ions, Sr2 plus. So 0.120 molar, but hold on, because I'm adding this to, remember, we're going to combine that with, was it 400 mils? The solution that we created up here was 400 mils of silver chromate with this concentration. So 400 mils of 0.00150 molar chromate, right? So we have to recognize that we're mixing two solutions together. So in order to get my concentration of strontium, we are combining two solutions. This is a solution, C1V1 equals C2V2. So in order to get the concentration of strontium, we have to do a dilution. So concentration was 0.120 molar. That's the original concentration, and we had 1 milliliter of that. The new concentration is what we're interested in. What is the new volume? Well, we combine together 400 mils and 1 mil for a volume of 401 milliliters. Divide both sides by 401 milliliters. This cancels. 401 milliliters. Milliliters cancels. And my new concentration of the strontium is going to be 3.0 times 10 to the negative 4 molar. So this is the concentration of my strontium ion, and so I can plug that in. So 3.0 times 10 to the minus 4 molar. Now the question is, what is my chromate ion? So I did add 1 mil into this solution, but into 400 mils. So technically, we should do a dilution equation, but that 1 milliliter probably won't make a difference. And you can check my math on this, but the chromate solution is going to be 0.00150 molar. It is not going to make a difference, so you can check it, but I'm pretty sure it kind of rounds anyway. So there we go. So that's my Q value. And I solve for Q, and you end up with 4.5 times 10 to the negative 7. So what I am comparing here is the Q value versus the K value. Okay. Anything, so if we think about what's going on here, anything, if I have too many ions, if I have too much of this, it's going to force the reaction back towards producing solid. So too much of this forces it right, creating a bunch of solid. So the KSP, I have to reach this threshold. So I need more than this. In this case, if we take a look, we see that what happened was Q is actually less than K. So therefore, not enough ions to precipitate a solid. I need more. I need more ions. The more ions I have, remember, it's always going to achieve K. It's always going to reduce itself to K. So Q is less than K, and therefore no precipitate. No precipitate. Yeah, that's it. That's the solution. That's the idea. Q is just less than K. All right, perfect. Moving on. So last little bit here. Consider the addition of the following solutions to a saturated solution of silver chromate with excess solid present, basically saying that there is excess. So we're going to predict two things that we need to look at. Predict whether molar solubility will increase, decrease, or remain unchanged, and why. So those are the two questions we're going to ask. Does solubility change, and why? Okay. All right. So this is asking about solubility ultimately. So we are again dealing with this silver chromate reaction, Ag2CrO4 2 minus. So let's just think about this for a second. Solid is in equilibrium with two silver ions plus chromate. Again, if it's no tag, it is aqueous. So if I add any of these, the reaction is going to shift back and produce more solid, decreasing solubility. If I lose either of these, the reaction is going to have to reach K, so it's going to force it to the right, trying to replace what it lost to get back to the correct ratio. So losing or gaining these, this is all Le Chatelier's principle. It's always Le Chatelier's principle. Okay, so when we deal with this, how does everything affect this reaction right here? So we're going to keep coming back to thinking about how it affects this chromate reaction. Okay, so that's the frame of reference. We're always going to come back to this and say, how is it going to affect this? And that's going to be our why ultimately. All right, so when we look at these two things here, it really produces 1 molar potassium chromate. What I always want to do is I want to divide it up into its two parts, if there are parts here, potassium and chromate. Yes, I recognize I have two potassiums, but all I really care about is the fact that it's potassium. Group 1 if it forms a strong electrolyte, so let's think about what's going to happen. It's actually going to make it much easier for the rest of this too. So if I think about these two things versus the reaction that I have, well, I have potassium, right? So the potassium can interact with the chromate. That's what it can interact with. The chromate is actually already present. So I guess perhaps we're going to do this on the next one because that doesn't, we already have, first thing you should look for is, in fact, when we're doing this, is one, do I have a common ion? So that's the first question. And we do. Chromate's a common ion. So what that's going to do is adding chromate is going to increase the concentration of the chromate. Okay, because I've increased the amount of chromate, that means this goes up. It's going to shift towards the addition. Oh, it's going to shift towards the addition. Okay, so if we are adding this, the reaction, sorry, shift away from the addition. So we're going to shift to the left. So by increasing the amount of chromate equals a shift to the left, which equals an increase in the amount of solid, which equals a decrease in solubility. That's our reasoning behind it. We have a decrease in solubility. Why? Because a common ion is present and Le Chatelier's principle. Okay, so that's the first question. Do you have a common ion? So if we look at the next one, again, I'm going to look at what I have here. I have H plus and I have nitrate. Are either of those a common ion? No, neither of those is a common ion. So the next question we have to ask is, if the common ion is not present, the second question is, will they react with an ion? And this is the important part. Will they react with an ion to form a weak electrolyte? That's the important part, forming a weak electrolyte. Okay, so I have two things. I have H plus and NO3. So H plus could react with which of these two ions? Well, H plus is not going to react with another positive, so it could react with chromate. H plus plus CrO4, 2 minus, will balance this out, makes H2CrO4. This is an acid. Is it a weak or strong acid? This is a weak acid. So because it's a weak acid, when a weak acid forms, it sticks around, right? That's what we know, is it doesn't dissociate. So by forming the weak acid, we essentially are forming the weak acid and it's not going anywhere. So the H plus is essentially removing the chromate from solution. So this ultimately has the effect of decreasing the amount of chromate in solution. This means we have to shift to the right to replace what we lost, which means a decrease in the amount of solid, which means an increase in solubility. Why? Because the formation of that acid ultimately leads to needing to losing chromate, and therefore we need to shift to the loss. Okay. The other thing that we could react was nitrate. NO3 minus could react with the silver ion to make AgNO3. This is strong. If you have a strong electrolyte, what we know is as soon as these two come together to form silver nitrate, immediately if it's strong, this just dissociates again and goes back. So ultimately, this process of forming silver nitrate immediately goes away. So by forming silver nitrate, it immediately goes away, and the amount of nitrate and the amount of silver does not change in solution, so there is no change to solubility. So yes, the H plus decreases or increases solubility. So the first one decrease in solubility, the second one increase in solubility because of the formation of the chromic acid. All right, next one. So again, same idea is how is it going to affect silver in chromate, and therefore how is it going to affect our equation? We are going to divide this into two parts. This is going to be divided into sodium ions and cyanide ions, Cn minus. Are either of those a common ion? No. Okay, so we can toss out the solubility change because of a common ion. So now we have to look at anytime you have group one, immediately we know that that is going to be a strong electrolyte. So we can immediately get rid of group one because it's always strong. So we can just eliminate that. Always strong. The cyanide ion could mix with the silver. So I could combine the cyanide with Ag plus Cn minus. Would anything happen? Well, yeah, it turns out two of those cyanides could come together to form a AgCN2 complex, still aqueous, but it's forming this complex. So what we ultimately have is the complex formation. Well, what's the K for this? If we look at the KF for this, it is 1.0 times 10 to the 21st. This is massive. So what this says is every single silver and cyanide, two cyanides that find each other, you will absolutely get product. This is super heavily product favored, heavily product favored. So this will form. In essence, what this is doing, though, to the equilibrium is the silver is getting gobbled up by the cyanide. Therefore, the amount of silver in concentration of silver in solution is decreasing. It doesn't matter that it's now silver cyanide because it's no longer just the ion. So the amount of silver decreases, the amount of silver decreases. So if this goes down, the reaction is going to shift towards the loss, and we are going to lose solid in order to increase the silver ions again. And so by decreasing the amount of silver equals a shift to the right equals a loss of solid or an increase in solubility. So we have an increase in solubility for this one as well because of the formation of a complex. All right, the last one, water. So this one is a bit tricky. Water is a little bit different. So as a word of warning, when you see water, it is never in an equilibrium because it's always in a liquid state. So the equilibrium is going to be important, but not why, because not what the reason you think it is. So my KSP here is concentration of silver ions squared, concentration of chromate ions. There we go. Okay. So when I'm adding water, let's not just screw around here. Let's add a ton of water. Let's double the amount of water. So really what we're doing is when you add water, you're actually diluting. You're going to have a dilution. Okay, I guess we spell it. Dilution. You're going to have a dilution. So what that ultimately means is the concentrations are going to change. So you have to think about how concentrations change. Water is never in the equilibrium. Okay, so what happens is it changes the concentrations. So if we look at this KSP, let's just pretend, just to make our numbers simple, and you can always do this. If the concentration is 1 molar for the silver, and the concentration for chromate at K is 1 molar, your KSP is equal to 1. Okay, so we're just pretending that our K is equal to, our KSP is equal to 1. Okay, so that's the assumption. That is the assumption that we're going to make, or that's just kind of the setup we're going to have. Because ultimately, I don't really care what the K is as long as we have it in reference to something. And so what we're going to say is, well, what is Q once I add this water? So we are going to 2x the water what that ultimately means is 1 molar concentrations by doubling the concentration, 2x the water, we're diluting by twice. My Q is going to equal, again, silver squared, chromate, 2 minus. So if I double the water, my new concentration is 0.5 molar squared. And both of them are going to be half their original concentration, zero point 0.5 molar squared. So if I solve for Q here, I see it as 0.125 versus 1. So what happened? Q is less than K because Q is 0.125 and K we set to 1. So therefore, what has to happen? Well, because Q is less than K, we need more ions to reach K, and we have the solid to do it. So equals a shift to the right in order to increase ions until K is achieved, which ultimately leads to a increase in solubility. That's it. So we increase solubility by essentially diluting it. And that's what you'd actually expect. If you had a bunch of, I don't know, sugar and water and you added some more water, more of the solid sugar would dissolve, right? Or more of the salt would dissolve. That makes sense. But this is the actual reasoning for the it's because of a shift in Q, because of the dilution, because of the change in K. So there's a handful of reactions that this will affect in different ways because if I only have K, sorry, I only have the products here. We don't have reactants because it's a solid, but there are some equilibriums where if you double the amount of water, it will shift it the other way. So you always have to just think about concentrations, not water. Water is never in equilibrium. All right. Hope that helps. And yeah, more to come.